Several years ago, I read a passage in a book that kind of stuck in my brain, and I didn't know exactly what the significance of it was at the time, but I knew that there was something significant about it as it applies to preservation work today and now. This has to do with saving a unplayable quad tape, and not playing the original unplayable tape, but transferring its magnetic image onto a playable tape. Now, that's nothing new. That's been around for 70 years or more. You know, that idea of contact magnetic duplication from tape to tape. But it had always been thought of and practiced as a way to duplicate or to make multiple copies from a master. So what I'm thinking about doing is doing that in reverse, sort of, in the sense that we are not working with a master going to a blank. We would be taking a finished recording and transposing it onto another tape. And that's a little different, you know, in the sense that in the duplicating process, you usually have a master of about 3 times the Oersted of the blank. So, you know, when you put them together and put a magnetic field on them, then there's no danger of erasing the master, you know, because your magnetic field is only enough to cause a transfer, a print onto a blank, which is a lower Oersted than the master, about 3 times lower, 2 to 3 times lower. And that worked well for many, many years, you know, high-speed duplication, you know, of all types of magnetic recorded tape media. But I don't think it's ever been done in the sense that I'm thinking about doing it. You know, here we're on the back end of things, as it is, you know, archiving. And we are, you know, more concerned with playing something that is unplayable, that's already been recorded. Well, there may be a way to do that. And I'm going to set out to try and prove it here, well, beginning in 2026. I don't know how long it'll take. But I think there's a way that it can be done. And, well, let me tell you about it, and we'll see about this thing. I'll read the passage from the book that I first became aware of this, and this was a book written by Ampex, the guys at Ampex Corporation, back in the 1980s, and of course that's been duplicated in many different books since. McGraw-Hill being one of them, the Television Engineering Handbook. So I'll put it on the screen here, but if you happen to have a book or obtain a book, you can read it for yourself. So this is dealing with videotape recording, and this is Erasure is the title of the paragraph. And this was contributed by H. Neil Bertram, which in the magnetic world, he was, is, I believe he's still living, one of the big brains in this realm. H. Neil Bertram. So it goes, erasure, the writing of new information on previously recorded media requires that the previous information be completely removed. Now, we all know that. Erasure requirements in terms of the previous signal to new signal ratio vary from -30 dB for digital systems to as much as -90 dB for professional analog audio. Video recorders, that's us, require about -60 dB. Erasure is the AC bias or anhysteretic process with zero signal field. If a reel of tape is placed in a large AC field, which is slowly reduced so that many field cycles occur when the field is near the coercivity of the tape, I believe they're talking here, then complete erasure is easily obtained. In addition, the largest amplitude of the AC erasing field must be sufficient to reverse at least 99.9% of the particles. That's the little magnetic particles in the emulsion on the tape, for -60 dB. And in practice, that field is about 3 times the coercivity. So if you had a tape with a coercivity of about 500, then the strength of your magnetic field that you're passing it through needs to be in the neighborhood of 1500 Oersted, or about 3 times the tape Oersted of 500. So 1:3 ratio. Now that's to get complete erasure. It's leaving nothing behind, in theory. Okay, let's read on. Most tape recorders utilize erase heads to remove old information before recording new data. Okay, we know that. Similar to bias recording, the requirements of the erase frequency is that the wavelengths be much less than the erase head gap to provide sufficient reversals of the particles. However, one important problem occurs with an erase head. As the erase current increases, the erasure level does not continuously increase as more of the MH loop tail is switched. There is an erasure plateau of about minus 40 dB for erase gap lengths of 1 to 2 mils and tape thicknesses of 200 to 400 microinches thickness. You know, you might think that's due to saturation, and that's what I thought, entered my mind first is, saturation. Well, not quite. And in the next sentence it goes on and says, this leveling is believed to be due to the phenomenon of re-recording. As the tape passes the erase head, the field from the portion yet to be erased, that would be the part of the tape entering the gap region, acts as a signal. That is, the field acts as a signal for the bias erase field to record a residual signal at the recording zone on the far side of the gap. That means as it's exiting the exit side of the erase head. And if you think about it, if you're making a field when you pass a current through the erase head, and that field is going to be in a circular or a cylindrical shape. So entering and exiting, you got a field on this side and a field on this side. It's the same field, but it's, in a cylindrical or a concentric shape around that head. And so what I take that to mean is the signal on the tape itself is interacting as it comes into the head gap region with the field, and it's modulating that field or disturbing that field in such a way as it exits the gap. The residual field on the exit side is re-recording what it just erased on the entrance side. Okay, then he goes on and says, this effect is seen only at long wavelengths compared to the wavelengths recorded on the tape. At a long wavelengths where the field is sufficiently high. Well, it is high because we're trying to erase the tape. It's more than sufficiently high. The problem is eliminated with double erasure by using a double gap erase head. Here they're trying to erase a tape. They don't want to re-record a signal they just erased. And so they grappled with that problem, you know, back when all this stuff was being, you know, invented in the 50s, late 40s, early 50s. To give you an example here, this is a double gap erase head from a VR-1000, and I don't know how good this camera will pick it up, but it's somewhat transparent, and you can actually see two faint little lines there. Now, that's not actually a gap in the sense that you think of a gap when you think of a recording head. What this is a ribbon of copper about 1/8 of an inch wide, and it enters and exits on the back of the head here. So it enters, and then it comes up one side, and then it doubles over at the top, and then it starts back down on the other side, and they're about 1/8 of an inch apart. And that's, you know, you're reversing the field around that copper ribbon when you double it and come back. The field is reversed. You know, the field that's formed around that copper when you apply a current to it. So there is, you know, the effect, or in effect, it is a double gap head in the sense that the field is reversed, you know, from this side to this side. And so it cancels. So you don't have that re-recording problem. Well, we don't want to erase the tape. We want to re-record. So what came up in my mind, you know, was what if I cut into this phenolic here and cut that copper ribbon there and brought it out to where you just have one wire instead of two. You would just have one field. And that goes back, you know, to what's being described in the book. You know, a single field erase head, which has that phenomenon or that problem of re-recording on the exit side what is being erased on the entrance side by the same field. Well, I thought about that, and I thought about it, and I thought about it. You know, there's something there that seems to, you know, strike a chord with me on some level, you know, that you could do something with that. I wasn't sure what it was at the time. This principle, or this phenomenon as they call it, was the whole basis of high-speed duplication. And in fact, the Ampex Corporation had built a machine in the I think in the late 60s, in the early 70s, called I believe it was an ADR-150, which was a high-speed duplicator for quad. And it could be added on to, you know, if you wanted to just make one copy, then you had the base machine, which held the master and the take-up, and then the blank and the take-up. Or you could cascade that into, I don't know how big they ever got. I think the biggest one I've ever read about or heard about was 6, where you had one master and 6 dupe stations, or 6 blanks, so you could make 6 copies at one time, one pass. And they didn't make many of those. I think 3 or 4 machines was about all they made of the ADR-150. As far as I know, I don't, you know, that's something I never had any dealings with, you know. But Bev did. He was there, and he saw it all, and he contributed some to that machine, the design and the development. So he explained all about that to me. And of course, what they were doing then, they were making a Mirror Master. And wouldn't you know it, Bev had a Mirror Master head for an AVR-1. Now, why would Bev, of anybody, if anybody was going to have a master mirror head, well, Bev would be the guy, and he had one on his shelf. And somewhere along the line, I had came into possession of a mirror image manual, and this manual describes utilizing the Mirror Master head and the driver cards, you know, for the higher head current to modify an AVR-1 to run backwards, you know, to produce a metal master, or a Mirror Master as they were called. And so having that bit of information on the mirroring, you know, kind of was another piece of the puzzle, you know, that fell into place, and I could read and study some about that. This all sounds very good, but, you know, if we're talking about taking a modern tape, which would be modern meaning 50 years ago, or modern meaning the late formula, is it all just academic? Because we would have to have a, you know, if we were considering that to be our master now, we would have to come up with a blank tape of much lower Oersted. How would we accomplish something like that? You could use the early iron oxide tapes, late 50s, early 60s, mid 60s. the ferric oxide, iron, the old orange, red iron tapes. Those tapes have an Oersted rating of around 300 to 350. And if we were working with a modern or a late formula, those have an Oersted of around 600, 700, 550, maybe 450 at the lowest. So you do have a window there of about 150 Oersted between 300 and 450. So you have about 150 Oersted range there that you could play with without, you know, getting in too much danger of erasing your original. And I thought about that for the next several years, 2, 3, 4 years at least, off and on, you know, how would I do that, and what would be a scenario? How would you, you know, and well, I started researching, and of course online is like, you know, just anything under the sun you can research just about nowadays. This is December 1949 electronics. And wouldn't you know, somebody went and did it and described the whole thing, how they did it, you know. Now, of course, we're talking about audio in 1949. You know, it's the same principle, basically. Well, this is, I guess, the earliest publication that I've found to date on the subject. You know, one thing leads to another. The next place it led me was to my old friend Clive McCarthy over in the UK. And that led to this. And this is from the research department. And it is accidental printing between the layers of a reel of magnetic recording tape. I believe this was 1950. Yeah, June of 1950. When the BBC was trying to figure things out over in the UK. And this is tape stored on a shelf over time. You know, the adjacent layer would print through crosstalk, and you would hear a faint signal on the neighboring or the adjacent layer of tape. It's similar, it's related in a way, you know, interaction. And now we're talking about very, very minute magnetic quantities here. So it doesn't take much you know, to have an effect over time, less than you would think. So that was an interesting side trip there to learn a little bit about what those guys had to say at the time. And then in 1969, some of the guys at Matsushita in Japan, they came out with a interesting report. In which they are experimenting with making a single copy by winding the two tapes onto a single reel and then passing that reel through a magnetic field to effect what H. Neil Bertram described as the phenomenon of re-recording. So I thought about that, and that seemed to be, you know, something more akin to what I was, along the lines that I was thinking, you know, of taking one unplayable tape, putting it with a blank, and in this case, a early iron oxide 300 Oersted, and then causing a transfer from the unplayable onto the playable. Okay, what does that look like in the real world? Well, let's see. Here we have a reel of a sample of our modern day, which is carbon back-coated late formula cobalt doped iron, and so we will call this our unplayable, or our master, which has an Oersted of about 600, 550, 600, 700, if, you know, maybe down to 450, depending on the brand and the type, you know. But it's between 450 and around 700, in that range. And here we have our sample of the old shiny back Mylar, non-back coated, the early red iron with ferric oxide tape from the early 60s, late 50s. And this tape has an Oersted rating of around 300 to 350. So it's almost 2 to 1, the Oersted ratio between the late formula cobalt doped tape and the early formula red iron ferric oxide tape. It's roughly 2 to 1, maybe a little less. But, you know, the late formula is significantly higher than the earlier formula. So if we go to the route that the fellows at Matsushita had worked out in their patent proposal, their actually, I don't know if this was a patent. It was a IEEE paper It came out in September of 1969. And I don't know if the camera is going to focus on that or not, but you can look all this up online for yourself. But anyway, what they were saying, if we put that in practice, what we would have is a single reel consisting of 2 tapes. And we're winding them with the oxides in. So it's oxide facing oxide pressed together. And that's what we have here. There we go. So that's our master and our blank wound together on a reel. Well, okay. So you pass that through a magnetic field, a field of long wavelength, and we get our transfer. And what we get back on the other end would be a reverse image, of what we had on our unplayable tape, or our master in this case. So it would be reversed on this tape, our blank. Now, that's backwards of what the ADR-150 did. Back in its day, we used an AVR-1 that was modified with a mirroring kit and a mirroring head to make a mirrored master, which is, a fancy way of saying a backwards tape. A tape that's recorded upside down and backwards. So that when you put that tape in contact with the blank for duplication, it produces a standard image on the blank. So you can put it on, any machine and play it. And, well, so what we've done here is we went right in reverse, and we have made a mirror image on our blank. Now, what that means is I'm going to have to build a transport in order to replay the dupe, or the copy that I made from the original. And therein is where some of the work, or a lot of the work lies, is to do that in hardware. Now, the electronics doesn't change because we're playing only, we're not recording. So we don't need to worry about higher recording currents, as if we were making a metal master, back in the day on our mirroring machine. We're not doing any of that. We've just made a mirror image, and now we need to play it back in order to digitize it on a computer. That's maybe a lesser problem, but it's still a problem, you know, that we have to work out mechanically in hardware, and all that in order to get the image off of our blank that we made from our non-playable tape. Exploring this a little bit further in depth, what's actually taking place or what needs to take place. If we look at our original unplayable master tape here, this would be coming off the reel, and this would be the inside or the oxide side, and this is the direction of travel past the head. And up here at the top you have the audio, and down at the bottom you have the control track, and then you have the slanted video tracks that are slanted because of the rotation of the head drum from top to bottom and the movement of the tape. So the tracks are laid down in a slightly skewed or slanted angle. Well, when we put that with our blank or our dupe tape, and then we zap it with our magnetic field and cause a magnetic transfer to take place, a duplication. Then we have a mirrored image of our original, and the control track. The video tracks are mirrored, and the angle in relation to the tape direction is reversed on our mirrored tape. And so therein is, the problem, the mechanical problem that we'll have to allow for and design our transport with this in mind. Now, if we look at this as far as in relation to the video head itself, then it would look like this. This is, a conventional transport, and this would be our original, and so the tape is going left to right through the head, and the control track is there at the bottom where it should be, and the audio at the top, and our track angle is what you would have for the drum rotating top to bottom as the tape moves past it. Okay, now that does not hold true with our mirror. Now, direction of the tape, left to right. The control track would be at the top, and the audio at the bottom. Well, that's not really a big problem, but you know, it is a problem that you'd have to solve by moving heads. The big problem is the track angle. It's reversed from the original. If we're going top to bottom and moving this way, then you can see it's exactly the opposite. Now, on the original, the AVR-1 Mirror Master machine, they compensated for that by building a head that actually ran and rotated in reverse, and the control track was mounted at the top of the guide instead of the bottom. So you actually made a true mirror image that could then be inverted and transferred on to a blank as a standard recording. Well, since we're not actually doing that, you know, we already have a standard recording. We're just wanting to get a good dupe, a magnetic image off of it onto a good playable blank in order to play it back and digitize it. So we're not going all the way, you know, as you would think of if you were actually making a mirror master for duplicating, but we're going, you know, part of the way. Well, in order to get around this, what we need to do is invert the orientation of the head, the position, in other words, 180 degrees. And on the transport, it would look like just that. You would be modifying the transport to mount a head upside down, as it is, or 180 degrees from, you know, the original or a standard configuration. And what that will give us then at that point is a way to play back our mirrored dupe. So here we have our blank, our copy, our dupe, and on our transport, our head is now 180 degrees flipped. It's upside down, and so here we have our dupe, still going left to right from supply to take up. Our audio is at the top where it should be. Our control track is at the bottom where it needs to be. Now the video track slant, even though, you know, it's completely opposite from the original track. Let's see, whoops, get our arrows right here. So we're still opposite, but now we're compatible with this new head position. See, our head is still rotating top to bottom as normal, and our tape is still going left to right as normal. And so as this tape is moved left to right on our transport, and the drum scans or traverses the tape from top to bottom, then you have a match of the track angle versus the tape travel in the drum direction, which is what we want. So it looks like from this point that all we really need to do in order to make our dupe playable on a standard machine is to modify the transport to turn this head 180 degrees and mount it upside down effectively on the transport. And that will preserve the relationship, you know, the mechanical relationship to the electrical or the magnetic tracks on our blank dupe, you know, our copy. Now, a couple things we'd have to pay attention to when flipping this head, positioning wise, that is the canoe, the tape canoe is formed here on this fixed guide, and here on the audio cue erase head stack. This is not a one-to-one flip in the sense that this screw is not centered. It's a little bit offset, so you couldn't just flip the thing over, you know. Well, that's one reason among many, but you would have to take into account the relation of this edge to this screw, or the center of this screw, or maybe the center of the head base. Or maybe another way of thinking of this in positioning would be if we had a point of reference, say this, or maybe this edge of the transport, when you take this fascia off and get down to the actual casting, then you could go from this edge measuring to this edge, and then this edge up to the edge of the head wheel, and you would need to match that distance when you invert this head in order to preserve the canoe of the tape, as they call it. And likewise with this head assembly here, since this is forming the canoe on the exit side, this head stack would have to be also flipped around. And now when you invert one of these, it's a little different from this in the sense that this is the audio cue erase, and this is the audio cue record play. If you invert this, you're actually swapping ends, the audio record play is going to be in this position. Now that's going to throw you out of lip sync with the recording. So in addition to flipping this stack assembly, you're going to have to also swap ends with the stacks themselves. So when it's flipped around, the audio record play will still be over here at the same distance from the head wheel as it were originally. So there's a little bit more to just flipping this 180 than just the head itself. You know, some of these other things come into play. Most notably is the canoe of the tape has to be maintained. Actually, the position of the control head, whether it's on this side or this side of the guide, doesn't make any difference. As long as it's there and it can read a pulse, it doesn't matter where it is, for the reason that we're not running in auto. You know, everything is horizontal lock. So we're not looking for the framing pulse, or we're not trying to vertically lock the tape. The time-based corrector at the input of the computer capture does that for us. So we don't really need to do that here. And in fact, the machine will lock up a lot faster and maintain a better lock in horizontal than in auto, just for that reason that you don't have that circuitry involved and that extra time it takes to lock up for the machine to find the track or to find the framing pulse, which tells it the track that the vertical information is recorded on, you know, so it can lock the vertical interval to the on the tape to the vertical interval on the house sync. You know, that's important if we were mixing, you know, through a visual mixer or, you know, some situation like that. We're not doing that, so we don't care. You know, and it doesn't help the machine play any better by doing that. In this case, simpler is better. To go a step further here, you know, on an unplayable tape, the problem with the playability is this rotating head against the tape. You know, if the tape is decomposing or has some problem, you know, with shedding, you know, and head clogging. Usually the audio track and even the control track, if it doesn't have a damaged edge, is never the problem. So, you know, the audio on an unplayable videotape, you can still, most cases, can play that just fine, you know. So you can actually pull the audio off of the original, you know, either in this process or beforehand, and make a separate audio file on the computer. And of course, when you get the video digitized, then you can go and edit the audio file back into the video, you know, and line it up and get it synced. And so that this is not really an absolute and mandatory thing as far as the signal is concerned. It is mandatory as far as the canoe is concerned, you know, the tape being properly oriented as it goes through the video head. And so, you know, the audio can be done at an earlier time or a later time, because usually that's not the problem with a problem tape. You know, the problem happens is when this spinning head rubs against the tape. That's when the problems begin. And actually, if you were, you know, doing all this in real time, which is the whole object of having a real-time playback, in order to assess or adjust, you know, the levels of our field or whatever, you know, to get the best or the maximum transfer without erasing the original. And really the only way to be able to do that is if you have a way to play back the dupe in real time as it's being, you know, duped. So even the control track, you could use the control track from the original, you know, in syncing up this drum to the dupe. You know, since they are in essence locked together mechanically, either on one single reel or two reels that have been pressed, you know, together. So you could conceivably even use the control track from the original if it doesn't have edge damage or something like that, to sync the playback of the dupe in real time as the tape is, you know, reeling through to the take-up side. So that's even a, you know, a possibility of doing that. Although it's probably would be easier to just go ahead, you know, and use the head that's already here. You know, since it's already a part of the video head assembly, there's not really any reason not to, unless you have some sort of a problem with the wavelength on these long wavelength longitudinal recordings versus the short wavelength rotary recording. There could be a problem arise there, you know, in the actual magnetic printing, the transferring, versus the frequency and the amplitude of the exciting field, you know, that we're using to actually do the print with. That could be a problem. That remains to be seen, you know, and we'll just have to work through that when we come to it, you know, if it is a problem. But there's ways, you know, around that. That's kind of where I'm at now, is thinking of what I need to do, the next step and the next step, in order to do that. And, you know, it's kind of an advantage in a way if that part was made first, because not being sure about the first part, the actual making of the magnetic print onto the blank, You know, there's 1,000 ways that could fail, and you know, there's a lot of variables there. Well, wouldn't it be nice if there was a way to build the transport in such a way as you wouldn't have to do the sandwiching or the compositing onto one reel, but you could do it in the sense of the ADR-150 as to have a master transport and a blank or a dupe transport. And immediately after you go through your field head, take your dupe tape and run it through the reverse playback head. So you can see in real time, or almost real time, the effect that your field is having, whether it needs to be increased or decreased. I could see where that could be very beneficial in knowing that, you know, in real time. Maybe as a setup aid or a calibration aid, you know, because every tape is going to be somewhat different. Number one, depending on I guess the make and the manufacturer and the model of the tape, the line of the tape, you know, and there was a bunch of them. And number two, the intensity of the recording that is on the unplayable tape. That's going to factor in also. So it would be really nice, you know, to have in real time the reverse head playing back the duped tape that you just made from the unplayable master. I could see many advantages in having that available. So that's probably the direction I'm going in, and we'll just see how far I get, I guess, and I'll keep you posted with some videos once in a while as to the progress. But I found it's a very interesting problem, you know, and it's somewhat beneficial in the sense that everybody or every archive or, you know, whoever or whatever, they've got at least one unplayable tape somewhere that everybody else has given up on, you know, due to erosion or decomposition, you know, that makes it just impossible to play it back anymore. And this looks to me like a fairly doable and inexpensive way to maybe get the information off of the old unplayable media and transfer it magnetically onto a playable media for digitization. And there's nothing new. It's all old technology and old ideas. I think maybe I've just found a new application for some of it. And we'll see where it all leads.